All right, looks like we're on. So today we're lucky to have our own Anne Boesgaard, who's going to give us the talk that she gave at the Keck Science meeting, which I think only Sam was able to see. So thank you for agreeing to give it here.
Okay,
Take it away.
thank you. Almost everybody at this meeting showed some picture of the Keck telescopes, but I think this one is the best because it shows Haleakala in the background too. So I want to ask the students here, who knows who this is? You do.
Tycho Brahe, from the picture. This is Tycho Brahe.
They wanted me to do a little history, but I don't think they wanted me to go this far. But here is Tycho. He's a Danish astronomer. You see something funny with his nose. He lost part of his nose in a duel. Anyway, the point of this is that he was given this whole island of Wien between Denmark and Sweden by King Frederick and established this observatory there. And the reason this is interesting is because it was the site of a large telescope meeting in 1996. And while I was doing some politely called decluttering, I found some old view graphs. This is the Large Telescope Symposium, and this is a comparison of the segmented mirror types like Keck is with a monolithic mirror type. And this is in 1996. All these projects started in around 1984, but by 1996, Keck 1 had been being used for astronomy for 2.5 years. Keck 2 had just been dedicated. These monolithic mirror types were on the way, but slow. Only one of the 4 BLT blanks had been done. The Subaru blank was being polished, and the Gemini blanks were on their way. But this was a big difference with Keck, that they got a real heads up, in part due to this guy. This is Jerry Nelson, who invented the whole concept and followed it through relentlessly. He finally had to move his whole family to Boston to sit there with iTech to make them do these mirrors. And it was partly due to this guy who came to Hawaii in 1966 to build the 88-inch telescope and the NASA IRTF. And ultimately, he started in 1984 with Jerry Nelson working on the 2 Keck telescopes. He also designed and built an endless swimming pool for me, so I do all my exercises 4 hours. So that's what the mirror looks like. It's these nicely conjoined hexagons. But mirrors don't grow as hexagons, they grow as circles, and they have to slice the ears off. When Hans retired, he was given one of those ears. And my cat, Jasper, thought that was the greatest place to get the ocean view. This is sitting on the windowsill in our house. And you can get a sense of the size too, although Jasper's a pretty big cat. Jasper is also the one I caught. So I was making use of high-res. Here's Steve Vogt, who was the PI of that project. And the project got upgraded from 1 CCD to 3 CCDs in 1994. And that was an important upgrade. So this is a distribution of the chemical elements in meteorites. And I have this squared off here, lithium, beryllium, and boron. So you can see how pathetically low they are compared to their neighbors on the periodic table, hydrogen, helium, carbon, nitrogen, and oxygen. but they contain a lot of information for us. So 2 lithium atoms for every billion hydrogen atoms, and yet there's only 26 beryllium atoms for every trillion hydrogen atoms, and not very many boron atoms either. So because they're so rare, the only way we can observe them is in the strongest lines of the spectrum, and those are the resonance lines. And for lithium 1, the resonance doublet is at 6707. For beryllium, it's ionized beryllium, and the doublet is basically the same atomic configuration as lithium, is at 3131 angstroms. We don't do boron up there in the atmosphere. So I want to show you why it's good to use these things to understand the inside of stars. The first place, this is a standard model of the sun, and this little red line here indicates if a lithium atom, which is on the surface, makes its way down to that red place, it gets destroyed. It sees a proton and immediately turns into 2 helium atoms. Beryllium has the same fate, but it's a little more resilient. It doesn't get destroyed until it goes down to 3.5 million degrees. So there's a very narrow shell of lithium, a somewhat bigger shell of beryllium in a star, in a main sequence star. But then the main sequence star becomes a red giant, and this little shell here gets expanded. And so what is left on the surface gets diluted, not destroyed, but it's diluted. So that's the fate of lithium and beryllium. They get depleted on the main sequence and diluted as they go to be red giants. So how do we observe this? Well, here's the lithium region. This is the lithium doublet, it's blended. And these other things are iron lines. Lithium is easy. Anybody can do lithium. But beryllium, look at this. It's the same doublet, but it's here and here in the midst of all that other fuss and fuss. So it's harder to observe, and it's harder to analyze, but rewarding, as we will see, because this 10 angstroms of beryllium can be expanded out, and we can do a spectrum synthesis and measure, map all of this with this synthesizing the spectrum. And so this beryllium line stands out pretty clearly. This one, we have to also look at this line. It's a line of OH, and it blends with the beryllium. And if you don't take into account that, then you don't get the same beryllium for the 2 lines. But it also means you can get the oxygen abundance. And there are several other OH lines in this region of the spectrum. And so, yes, we got the oxygen abundance. And we could do that because of this 3CCD chip. The quantum efficiency at 3130 is 93%. Better than it is in the other wavelengths. So this was a tremendous boon for people like me who wanted to go down into the ultraviolet. So we had embarked on this project, Big BE project, and that's the name of the directory on my computer, Big BE. We had 17 nights allocated over a 6-year period. One we lost to a snowstorm, one we lost to 2 earthquakes, and that was something else that I was getting ready to go observe that night, sitting at home, 7:07 in the morning, and the house starts shaking. And then 7 minutes later, it started shaking again. In the meantime, I'd run outside, so I didn't understand how badly the second shaking was, but it was a 6.7 magnitude earthquake right off the Big Island. And the second one was a 6.0, 90 degrees from our house. It was the second one that knocked the china out of the cabinet. Anyway, so this is a rundown. We got 117 stars, and we managed to get down to minus 3.5 in metallicity. What we did, we measured a lot of iron lines, we measured a lot of titanium lines, and 3 magnesium lines, so we could determine their chemical composition of those things. And then, as I said, we did a spectrum synthesis for beryllium, and we also got oxygen abundances. And here we have beryllium. It's a logarithmic scale on the basis where hydrogen is 12, so beryllium is 1. And here's iron over 4 orders of magnitude. We got a really nice relationship between beryllium and iron. Not particularly expected. But while we were up, we looked at beryllium and oxygen, which we might have expected to be correlated. And I'll explain that a little bit later. And while we were up, of course, we looked at oxygen versus iron, which is a remarkably nice relationship also. But then people do this all the time. They do a chemical element compared to iron, compared to the sun, compared to iron. And so this shows a steady increase as you go to lower metallicity. But as we say here, at low iron, oxygen over iron is 10 times the amount that it is in the sun, which is very interesting. How do we make so much oxygen so fast? And while we're up, we can look at titanium. Look at titanium and iron. That's a remarkable correlation. Again, down to iron abundances of minus 3.5. And while we're up, look at magnesium. Same nice relationship between those. Now I'll come back to this, but let's look at the lithium. Lithium is made in the Big Bang. Hydrogen, helium, and lithium are made in the Big Bang. But that's when the temperatures are 4 billion degrees and it's a Big Bang and it expands, and after a while they quit making any elements. But there is some lithium, and maybe you can see from here, this is the line of the neutrons. So they go down to make these other things. This is the line for deuterium, but then deuterium gets eaten up. After about 15 minutes, it doesn't change much. Those abundances get locked in. And that beryllium-7 is unstable, it doesn't last. It becomes lithium-7. Anyway, we get hydrogen, helium, and a little bit of lithium. But nothing else, fortunately, because if we got helium and the protons that come together, we make a lot of helium-5 or whatever we would call it, and that would be the end of that. Same thing with beryllium-8. We can't put 2 helium atoms together and make beryllium-8, except under very special circumstances inside stars, where we have what we call the triple alpha process, and it has to be 3 helium nuclei. all at once to get anything. So fortunately, there is no stable mass 5 or mass 8, so we're here. Okay. So this is what I showed you, beryllium versus iron. This is what lithium looks like. It doesn't go up like that because it has this primordial component to it. And then it starts building up above that around -1. But there's a very different background because lithium is formed in the Big Bang and persists, whereas beryllium, well, just a minute. Beryllium, all three, lithium, beryllium, and boron, are destroyed and diluted inside stars. So they have to be made someplace outside of stars. And the outside place is with galactic cosmic rays, 150 MeV or so is energetic enough to break up hydrogen, to break up carbon, nitrogen, and oxygen into little pieces, among which are lithium, beryllium, and boron. So that's how we make that stuff. Galactic cosmic ray spallation. So we're going to look for primordial lithium. We want to look in the older stars. But we don't know the ages of stars very well, but we do know the ages of cluster stars. So we can look at globular clusters. We want to look at metal poor stars, which are also globular clusters. And we certainly want to look at unevolved stars so that they haven't had chance to deplete or dilute the lithium. So we started looking in one of these clusters, M5, and this is the HR diagram for that. These are where our 5 stars were, and expanded through here, where you can see they're at 18th magnitude. And to get high resolution spectroscopy of 18th magnitude stars takes a big telescope like Keck. Takes accumulated 5-hour exposures. This is a different cluster, but it shows you the lithium line synthesized, and you can see already there's a difference in the strength. So this is the best fit to the observations, which are the black dots. The red lines are factors 2 above and below. And if you look at just those 2 stars, they're 10 degrees different. And look at that difference in the strength of the lithium line. So what's going on here? How are we going to figure out what's the primordial lithium when they're not going to be telling us? And that's what happened. These are a number of globular clusters plotted against their metallicity. And look at that. So these are just the various references to those works. Here's that figure again. And you can see that they all show a range. These are all unevolved stars, either main sequence or just turn-off stars. And they all have many of their stars against above what we were measuring in the everyday halo field stars. So none of them are up here for what is predicted by primordial lithium. And the maximum is all about the same for all of them. It's about 2.5. Does that mean maybe the theory should get a little tweaking? Or does it mean that they have all reduced their original amount from yet a higher amount? This one shows you that age doesn't seem to have very much connection. Those are the ages left to right, and all we can say is that and 71 is the youngest. But why globular clusters are supposed to have had multiple generations of star formation. So we see on the main sequence of globular clusters stars with that looks like they've been affected by a supernova or two. But yet, if that had happened, there ought to be stars with no lithium at all. And there aren't, except in this one cluster, there's maybe 3 or 4 stars that are only upper limits. So that is a puzzle. Unless lithium is made by supernovae, which is not very, it's not an idea that's in favor of much, not enough evidence for that. So what we hypothesize, along with very detailed stellar rotation models, is that all the stars start with some angular momentum when they're forming. Some have more than others. And as they evolve toward the main sequence, they slowly spin down and they redistribute the angular momentum and the material, and therefore they can lose some of their lithium. So some would lose more than others. The faster rotators would lose more. So that's a nice explanation for that. So we have done, I've just talked about these 2 big programs that we have done with the Keck telescope, one on primordial lithium and one on what's going on with the Big Bang. And I want to say this. When we so proudly publish papers, we need to know that there's a lot of people behind us making it possible for us to do that kind of research. First of all, to build a telescope like Keck took an enormous amount, and there's 300 tons, and it has to be able to move around so that it can find another star and stick on it with great precision. So, and people design exotic instruments and exotic software, and the people there who run the telescopes and people who do all the administration. And we all individually and as a group have to recognize how indebted we are to all those people. One last thing. Today, the autumnal equinox, 8:50 p.m. on Hawaii time. I don't know why the OX is not. Thank you.
How did lithium and beryllium get their names?
I think that's beyond the scope of my talk. I can tell you some more about Tycho Brahe if you want, and his unfortunate death, but I don't know. Is that all?
I'll throw you a bone, maybe. So you mentioned multiple generations of star formation in clusters. Have you looked at the lithium abundances between the multiple populations in clusters? Because if I recall correctly, there's a correlation or an anti-correlation with lithium and the different stellar groupings of globular clusters.
Very tough to get this in globular clusters. These guys who did that in the southern hemisphere, these guys on this cluster, they have the virtue of a spectrograph called giraffe, and they can get a lot of spectra at the same time. these guys here, but still they only found a few. I don't think that they found anti-correlations between sodium and lithium, for example. Southern globular clusters are basically brighter than the northern ones. 18th magnitude is a struggle.
Similar question, did they comment on the one upper limit in 6752? Like, what are the other abundances of that particular star?
It's not one star. There's something like 5 or 6 stars with upper limits in that paper. And I don't recall them saying anything other than it could be indicators of multiple generations. We should go look that up. Maybe they did. And there's also a recent paper by Evan Kirby. Some of you may remember him. He was a postdoc here. Anyway, he seems to have found evidence of one supernova that has managed to elute one of these clusters.
Is there an error bar on your primordial lithium dotted line?
Probably.
Yeah, what would be, if I reversed it, what would be the implication if that were lowered to 2.5, where everything else seems to max out? What would that mean for the Big Bang?
Oh,
Throw Eric under the bus.
I don't know.
You pointed out it's all peaks
it's
out at 2.5.
probably, they probably say the error bars or something like this. It's like 2.7 to 2.8. But yes, we need to call this paper and this diagram the attention of the Big Bang modeler. I did send one of them an email because FJ was kind enough to give me his email. He's not a member of the AAS, but haven't heard from him.
So when you're doing the synthesis for beryllium, how sensitive is that to? I know there's been a lot of back and forth on the different like abundance ratios for the sun, for instance. Are you affected by that, or?
Oh yes, I think beryllium is most sensitive to log G. Lithium is very sensitive to the temperature, but not beryllium. It's most sensitive to log G. And with the sun, the problem is where they think the continuum is. And of course, that's a problem, but less so. The more metal poor you go, the less problem you have figuring out where the continuum might be. So that would produce a smaller error for low metal stars.
You may have said this, but why is it you haven't been studying boron?
Because I'm not up and above the Earth's atmosphere. I have been studying it with, first with the Copernicus satellite. You people probably don't know anything about that. And then with the Hubble Space Telescope. But it seemed to be easier for me to get time on Keck than it was to get time on HST.
I have a dumber question, potentially dumber question. So to get the actual abundances, obviously you have to do a spectral model and take all of the stellar parameters into account. How are those models actually calibrated? Is it completely theoretical, or do they actually like do binary pairs of lower mass stars like you're measuring here and solar-like stars to actually pin it to a solar-like star metallicity?
The models we use are Peru's latest models. And we have to spend some effort trying to figure out the gravity and the excitation temperature. And we do those by measuring other spectral features.
But they're all theoretical stellar atmosphere models, or
Yes.
are they pinned down to anything
Well, we
Besides
send down
the
to
sun.
the sun.
besides the sun? Is that the only calibrator here?
No, they pin them, some models to Arcturus and some to, I can't remember the name of the B star. Or maybe it's Sirius, which is an A0.
Any final questions? Not, let's give Ann a round of